All right, and we are live. Welcome to this week's Chiller Questions Answered, if I can get the name correct. Hope you had a great weekend. Hope you had a good week last week overall. I know life's been pretty chaotic for me, so fun stuff. Kids are running absolutely rampant, so that keeps things exciting. Had a fire this last week, or had a. It wasn't too bad. It was a fairly small, but it could have been much worse brush fire. We got it under control. Um, and so far for a Monday, not been this greatest get day. It's just been we had a rough night last night. It's just been a rough go this morning. So my point being, let me have the bad day. Y'all have the good one. Go make a deal on that. I'd much rather it be I take the bad day. Y'all go have a really good start to your week. Get this going right. Get some chillers repaired. Whatever the heck it is we got to do this week. Let's just get it done. Yeah. That being said, I will give a disclaimer. I've been watching my network kind of through the morning here. For some reason today, it's just really struggling. So if it off and on kind of has these weird little glitches, I apologize. I do hope to be relocating maybe towards the beginning of the year. So if that happens, where we're looking at going, should have significantly better internet. If that is true, I haven't tested it to confirm it yet, but if that is true and it's a lot more stable, it'll make these things way more smooth. It has been one of my frustrations with where we're at now is basically where we get service for the internet is just barely enough. Anyway, I'm getting off on different tangents. We are here to talk chiller. So if you have any questions, feel free. Put them into the comments. I will answer them accordingly. I do have the first question already queued up, so I will start on that here in a moment. Don't worry about if it feels like too simple or too dumb of a question. Believe me, it's not. Chillers are a very complex and complicated topic. There's a lot that goes into them, and that includes the chiller plant, the cooling towers, the BMS control systems. All of those things are all encapsulated in what we're here to discuss. And when we talk about chillers as a whole, usually we are talking about just things revolving around them too, as an entire plant. Just like, for me, if I talk about an RTU, I'm usually also including things that might be within the ductwork and stuff as well. So now, in fairness, I might consider like a fan power box or a variable air volume VAV, something like that. Might talk about that on a separate context, but overall, if I'm talking about the air handler, I'm talking about the duct, right? If I'm talking about the chiller, I'm talking about the piping, the plant, the pumps. Similar concept there. So my point being, I really do want to take more time to focus on making sure that even these really basic questions are covered properly. And that's what we're here to discuss. So if you have anything at all, doesn't matter how simple or how dumb it might feel, please feel free to ask. And if I can't, for some reason, because it happens, if I can't get to all the questions, I do save them. We will come back to them at a later date. I will say that we had a couple of things, one in particular with a Dunham Bush centrifugal that we're still working on in the background, so I don't have an update for you this week. And as soon as I have one, it is a fun call that I think would be fun to loop back around to and discuss. So, anyway, like I said, if you have any questions at all, feel free to get those in. I just got an email in, actually, for one. Let's see, we are starting. And I'll have to circle back around to that later. Okay. Let's go to the first question. As long as I have proper design delta P, does that mean my GPM is correct? All right, so let's get a couple of acronyms here. So delta P, we're referring to delta pressure, meaning the pressure difference across our heat exchanger, whether that be evaporator or if we have a water-cooled condenser, either way. And then GPM is gallons per minute. So as long as the delta P is high enough, are we good? Not necessarily. No, that is not true. Many times so we use delta P. So our DP would be another way to say that. Be our diff pressure. And then our GPM is gallons per minute. All right, so these are, if we have our heat exchanger, okay, so let's say we've got this evaporator, and we've got a flange here and a flange here. We're going to take a pressure here and a pressure here, and let's say this was 10 psi coming in and 5 psi leaving. All right, psi. Okay, so in this context, we would say that's a 5 psid. In a lot of your chillers, 5 psid is actually within fairly normal range, especially on, say, air-cooled machines. It's very, very typical to see somewhere between a 3 to 6 psid typically. And that's a very, very common number. Don't use that as an actual rule of thumb. Most of your air-cooleds will have flow schematics in the manuals, like the IOM, installation, operations, and maintenance manual. So try to use that as much as possible. But for just a general sense, I'd consider 5 psid within a range. Now, when you get into water-cooled and centrifugal styles, that starts to change pretty quickly. But so having these pressures, checking it here at the flanges, can indicate, or does give us this pressure reading, which does seem to be okay. And if I saw this in the field that matched up with my GPM chart, I'd say, okay, we're doing pretty good there. Now, there are some things that can get in the way of this. The biggest thing that we'd need to be worried about is plugged tubes. Now, this could be intentionally plugged. This could be due to like calcification or anything of that nature happening. So by plugged, what I mean is, let's say we have our tube sheet. All right, so the tube sheet is at the end of the heat exchanger where we're coming in and out. We have our tubes. Now we may have it to where somebody came through at some point and identified that this tube right here was a problem, and they put a literal plug in it on both ends. Now this is plugging the water side of the tube, not the refrigerant side. Okay, so all of these conditions are going to be affecting the water side. So they decided to plug this tube. Maybe they decided this one was no good and this one was no good. So for most heat exchangers, I think you can get up to about, 10%? It's 10 to 20% of the tubes plugged before you start seeing significant issues. That being said, what this will do though is this will cause a higher DP for us, even though we may not have proper flow through the machine. And that's the point I want to get at here. If these tubes are plugged, we're going to see, say, normal DPs, or we're going to see higher DPs, even though our flow may not actually be there. Our GPMs through the machine might not actually be on track. So that's what we've got to be careful of here. If we don't know if the tubes are plugged, we're going to see other symptoms as part of what we're going to look at. If we truly have proper GPM through that machine, and our DP is good, we're going to have good approach values. So approach being the difference between the leaving water temperature and our saturation on the refrigerant. That approach value is going to be within range. Now, that range is going to depend on the evaporator itself. So some evaporators have a higher range, some have a lower range. That's something we can discuss separately. But a high approach even though you've got a good DP, would indicate a heat exchange issue. If you've got a bunch of plugged tubes, that's where that heat exchange issue is coming from, or it could be one of the reasons. Now, more than just it being a physical, somebody put a plug in, it could just be trash from the loop, calcification, bad chemical treatment. So these loops have chemical added to the water to prevent buildup, corrosion, things of that nature to accumulate in the tubes, causing a flow or heat exchange issue, fouled tubes, exactly. So it would be the exact same process here, right? These tubes can literally accumulate so much buildup in them that they stop flowing water, and they're hard to even get a brush through. So you'll sit there and you'll try to brush them out with a brush machine, say a Goodway machine, and it won't even go through the tube all the way. And like that's when it gets really bad. That's when you start to get like the conversation around having a chemical treatment done, where we're going to chemically flush this heat exchanger. But there are, to build on that a little bit further, more than just it plugging the tubes, part of what can happen is the accumulation inside of this. Say this is one tube inside of here, all right? We could have this wall of accumulation that builds up fairly heavily, and what that starts to do is it starts to choke down on the actual tube wall itself, makes the tube smaller and thinner. Again, all of these conditions are going to allow us to maintain what looks like a proper DP, where we've got good GPM. But in reality, not only are we losing heat exchange significantly, like we're going to be losing major heat exchange here, we're also going to be reducing the total GPM, even though our pressure differential maintains. So these are major conditions to be looking for, even if we have proper DP, but it doesn't stop there. Because if we cannot check the DP right here at the flanges before the rest of the system, there's lots of times it may be further up here in the piping. That's where we're actually getting our pressure reading from. And there's other devices in series there. There may be a strainer in the piping before you get into the chiller. So here at the strainer, or taking measurements before the strainer, but not being able to get them at the chiller flanges after the strainer, you may see a proper DP. But in reality is that strainer may be getting plugged up, and that's reducing flow, but it's artificially creating a higher DP across your loop, or across your heat exchanger, I mean. So those would be a couple of just major things you're looking for. Of just because you have a good delta P, good delta pressure, PSID, across your heat exchanger does not mean you are for sure good on the actual GPM through that heat exchanger. And being cautious of having plugged tubes, whether it be somebody physically plugged them for service, or somebody or they're plugged up due to, say, poor chemical treatment, poor maintenance practices, and they've got calcification or whatever debris stuck in there. Or you get into the strainer conversation where you're not actually checking pressures at the flanges. You're checking it somewhere in the piping, but there's other components. Another component could be a bypass of some kind. It's possible that if you're taking pressure readings before the bypass, and I've seen systems that are set up like this, and it's really easy, if you don't know any better, to take the reading in the wrong place. So if you're checking it before the bypass and that bypass is not working correctly, it's not supposed to be open and bypassing the heat exchanger, but it is a little bit. Again, that could give you relatively okay DPs, but still have a flow issue. These are all things to take into consideration, and it does not guarantee 100% that your GPM is good. And we have to look into the rest of these factors. Our heat exchange is going to be the big one. If we think we have good GPM, but we're still showing heat exchange issues, which is going to be found in the approach itself, that is specifically where we need to hone in on. What is the approach? If we have high approach values, even though we're supposed to have good GPM, we're still having a heat exchange issue of some kind. Now, there's other things we may need to rule out. We may need to rule out that there's no oil stacking in the heat exchanger. That's going to lower our rate of exchange. We also need to rule out any possible refrigerant charge issues, right? So there's other things that we need to rule out in this process, but we can do that through analyzing our data at the chiller itself. And then as we work through that process, we can eventually get to, okay, we need to open this up, check the physical tubes themselves. The tubes themselves may be the problem. It's a really good question. I see you there, Froggy. How you doing, Tom? What's up? Talk sweetly. Next week, planning on streaming. It's the 29th. Is it? Oh, it is the 29th. Oh, next week, so the September 29th is my birthday. I do expect to be streaming next week. Let's see. I will go out of town the week after that too, but I should still be able to make the 6th. So the 29th, the 6th. Yeah, I should be good the next couple of weeks on the stream, and we will get to have a birthday stream for me. I don't know what I'm going to do for myself yet. I did get an awesome early present for my family. So here, I'll show you. They got me this new keyboard. So I spend a lot of time on the computer nowadays, and I don't know. So this is a mechanical. This is my birthday for this year, and there's just something about it. I don't know. I've never been into this kind of thing a day in my life up until going into the academy and doing all this full time, and now having so this is the tactile version. I could get way off into the nerds here, but yeah, I'm very happy with my birthday present. Thank you, family. Thank you very much. Okay, I see you there, Kumar. I'm going to really struggle with that first part, so I apologize. So let's dive into train purge unit. Let's explain that. It's a really fun conversation. I think what I'll do, I'm probably going to just draw that out. Okay. Get a sip of coffee. Train chiller purge unit. Explain, please. Happily. I do. So we have another about the Earthwise purge. Yep. Let's dive into that. Especially after tower cleanings, if they do not shut down the pumps. Yeah, let's dive into this. This is a good topic. So let's talk about a purge. Let's first just do a quick discussion on what a purge is. I think that's really important to make sure we're very clear on. So a purge, that's not right. Purge, this goes on a low pressure machine and it removes non-condensables. Okay, these are on low pressure only. Now, why is it low pressure only? Well, that's because by the definition of low pressure, they operate below atmosphere. So that's how we define what a low pressure chiller is. The refrigerant during operation is in a vacuum, especially on the evaporator, but even in the condenser, depending on what our conditions are, how much load we have, what our condenser water temperature is, we may actually have both sides of our system down below atmospheric pressure. So with a high pressure system, meaning it operates above atmospheric pressure, what happens when we have a leak? Well, that refrigerant escapes out and everything pushes from inside the chiller out of the chiller. Well, in a low pressure scenario, it's the opposite, because our lowest pressure zone is inside the chiller. Our chiller is less than atmospheric pressure. So any leaks draw atmosphere in, and I do say atmosphere. So atmosphere has non-condensables and moisture. Okay, so there's H2O and there's nitrogen, would be the main one, inside of atmosphere. So both of these have to be managed, and we'll get into managing these, but it's really important to have an understanding of this up front. The purge specifically focuses on non-condensables. That is its primary goal. We have other components that focus on the moisture part of this aspect. So now that we have just a very basic understanding there, these are set up on a condenser. So let's first just kind of draw where these are out and location wise. So we're going to have a little purge pump up here. We'll have our little evaporator tank and so forth. All right. Where these are set up, we're going to have one line. So this is the chiller condenser. We're going to have one line coming down and tapping into the chiller vapor port, or midpoint on the condenser. We're going to have another line coming down and tapping into another midpoint. Now our discharge line is coming in over here. So we have the condenser, we have discharge line, and then we have our liquid line coming out. What's happening here is these purges they create a gravity feed. There's not a pump or anything that physically moves the refrigerant through here. Now we're starting off with just the basics of a purge system. So we're not cycling that refrigerant through a pump. There is a compressor on this system, but that compressor is a separate refrigerant circuit. We'll discuss that momentarily. But why would we come off of the middle of the condenser? Why would we not come off the top of the condenser? Because when we discuss non-condensables, we're always familiar with them stacking at they stack here at the top of the condenser housing. So why would we want to have that pulling off of a midpoint? Well, that's because during operation, the hot gas discharge refrigerant comes up here, and there's the distribution rail system up in the top of this, and that helps disperse all that high velocity discharge gas throughout the condenser to then make contact with the tubes and begin to condense down. Well, in that process, there's this zone in here where our non-condensables are going to stack during operation. So right here towards the middle of this. Once you get down below that, you start getting into liquid refrigerant consolidating, and then above that you get into, it's just the high velocity discharge gas coming in. So there's a lot of that high velocity gas is pushing those non-condensables down into more of a center point on the condenser. And this is why when the chiller is at a standing state, it's not on, the compressor is not running, those non-condensables will stack on the top up here. And that becomes a problem for the purge, because unless it is a severe contamination, it has a severe contamination where there is a lot of non-condensables, the purge isn't going to really pull that much out when the machine is off, because most of it is going to be stacked up here. So you could have it to where in an off state, you could run this purge and it says, hey, I'm not finding any non-condensables at all. So it never needs to pump out. But then the moment you turn it on, you don't get very far in the process and you start getting into major surging. That is because of the non-condensables then getting pushed down, and then they're at that point. Then with it running, you could have the purge turn on, start running, and all of a sudden it's drawing all these non-condensables out that prior to turning the machine on, it never registered that there was non-condensables there. That is why. Is during the on state, while the compressor is running, we push those non-condensables into this little zone here. And that's why with our low pressure centrifugals, we're going to see the purge pull off of a middle point. Now, again, this is a gravity feed, okay? So there is a siphoning effect happening as we're processing this refrigerant, where the discharge gas is coming up into the purge, up in the top of its evaporator, and then it's going to drain back out as a liquid back into the condenser, and then it's just going to recirculate back into the high pressure condenser or the high pressure refrigerant, and then it's going to continue with the refrigeration cycle from there as normal after it's been processed. So that is the basic cycle of how this is moving through the machine, where it's going to be connected. I know, and the main thing to understand is just where are those non-condensables at what state. So just be aware that if the machine is off, they're going to stack up here. And that's also where a portable purge really becomes handy. So most condensers will have a service valve on the top of them. If we have a portable purge, like what RefTech produces, I'd highly recommend theirs. We can come in here, and if we know we have a lot of non-condensables, but our built-in factory purge is not able to access them because of them stacking, and we can't run the machine long enough to actually process those down, right? So there's a lot of conditions where we cannot turn this chiller on and have it running even at an unloaded state. It's going to affect the load and the rest of the plant way too much. In that scenario, that's where we can connect a portable purge to one of these valves on top and create the exact same cycle, right? The exact same process is going to happen. It's just we're actually going to process the top of the refrigerant. But why would we not have a factory purge already built in to be able to do that during the off cycle? Well, in my opinion, that's largely because we should have tight machines. We should have properly maintenance machines. And if that be true, we need to be able to properly process the refrigerant with the machine on. These systems are built to run for days on end. They're not, while they can cycle on and off and shut down and do all those things, they're built for the customer to, when they turn on, unless you just want it to, it shouldn't have to turn off. And while we're running, this is just where the non-condensables are going to stack. They're not going to be up here. So then we'd have to build extra complexity into the system to where, okay, well, if the chiller is off, then I'm going to open this valve here and have the purge pull off of the top of the condenser, and it can still drain down here just fine. But then when the chiller is on, I'm going to open up to this one down here and pull off of that. There's this whole dynamic that doesn't have to be there, that we then open ourselves up to trying to do both. And the factories just don't do that. They're focused on when this machine is running. And if there is if something is going on that is severe enough that much non-condensables are stacking in here, that it would require having to pre-process the refrigerant by pulling off the top of the condenser, then something is wrong, something needs to be fixed, and they would rather push that customer to have that resolved before just having the purge constantly fix it for them. Because I've seen a lot of customers, if that purge will do the job, I mean, that's what they'll do. They'll let that run for forever, and they'll never fix and address the leaks or anything of that nature, and that's not good for the machine. It's not good for the oil. That creates an acidity to your oil. It wears your bearings down. Like, it has this multi-order effect by having those leaks, especially if they're that severe. So it's not that simple. And that would be my assessment as to why the factory takes that approach. Anyway, if we were to connect a portable purge, this is where we would connect it. We would just run the drain back to, say, the liquid line or some midpoint on the condenser, or another top point. But keep in mind, all this has to have a gravity feed. It's all gravity drained back into itself. All right. So basic layout: discharge gas. We collect our hot gas refrigerant samples at a midpoint here during operation. Comes up into the purge system, gravity feeds back down, drains back out. Now, let's get into the actual purge assembly itself. Okay. Let's see how good my artistic skills are going to be today. This is our evaporator. This is going to be called the Purge evap. And there's going to be a condenser over here. We're going to have our purge pump. Then we've got our drain. Actually, in that drain, we have a dryer. Okay. There's part of it. Now we also have, coming into here, it's MD for metering device. And then I'm going to use this one to represent discharge gas coming from the purge. So it's got its own little condenser. And that condenser then feeds into the metering device, feeds through, back. And then okay, so that, what else do I want to draw? Actually, I'll use green. So right here, we have a line that comes off into this pump, back out and away. Now this does not capture the, okay, I have a way, I will draw the Regen tank, the carbon tank into this here in a moment. We'll start off with just a basic, with just a basic purge, and then we will get into the newer style purges that have a carbon tank where we can recapture that refrigerant. Let me just see through the questions real quick here. Just make sure. Good to see you, Sterling. And Kumar, if there's any additional questions throughout this process, man, feel free to throw them in here as I'm talking through this. I want to make sure that I am covering our bases here. Talking about, I've been meaning to ask, I've been told when you have them usually travel through the circuit, you'll see pressures going up and down. Well, they usually settle in a particular place. In a regular circuit with no purge, I mean, yeah. Although I've personally never noticed it, I've always believed high head pressure is not necessarily. Yeah, I've not seen the up and down piece. Usually it's just a really high head pressure for a non-low pressure system like what you're talking about. That's been my personal experience. It makes more sense that they would just stack up in the condenser and stay. Yeah, exactly. Yeah. Yeah, that's Sterling. What you've seen, I haven't personally noticed the up and down things. Just when we start stacking non-condensables, they just stack in the high pressure side of the system, and it just throws the whole friggin' thing out of whack. Okay. Like I said, Kumar, feel free to add any other questions, and everybody else as well as I'm going through this. And by the way, I do apologize for the flies. We recently moved the herd through to a different pasture, and they have to pass by the house here to do that. They always leave a swarm of flies in their wake, and so it takes a couple of weeks for them all to redisperse and get rid of them. So I know we've got a fly buddy flying around here. I apologize for the distraction. Okay. So getting back on track to the purge system itself. What we have, purges have their own separate refrigerant circuit. And we can show this here if we want to take and see a physical view of this. Let me actually pull some shots of a purge up so we can actually see a live example. Let me get a good... This won't work. Actually, that one's probably better. Trying to moderate. Let's see. There's one other photo. I think I'm going to try to grab that one instead. It's a little bit of a better shot. Yeah, let's use this one. All right, so this is kind of give you a picture of... This one has the Regen tank right here. But just to paint the picture, this is our purge unit we're discussing. This is the evaporator. This black tar insulation here with some ice buildup on it, that is our metering device for this evaporator inside of here. This gray line right here coming up is feeding into the metering device. That is the liquid line for this little refrigeration circuit. This refrigerant is 404A in this particular unit, and this is a 123 low pressure centrifugal. So these refrigerants do not blend, they do not mix in any way. They don't make any contact with one another. So this compressor is moving through this little condenser, pumps up into the metering device, and you can't see the lines immediately in this shot, but here's the suction line coming back out of the bottom of the purge evaporator, and there on the back side here where we can't see it is where the refrigerant line is connected for the discharge gas, and then down at the bottom there's a liquid drain that's going to create the siphoning effect, and we'll talk through that in just a moment. Then this little solenoid here is one of the purge solenoids feeds into this pump, and this pump is what pushes the non-condensables out. Okay, so just to kind of give you a physical representation of what this will look like in the field. So, the chiller is going to send discharge gas into here. And this is all high pressure refrigerant. It's in some mixed state of de-superheating. It's at the top of the condenser bundle. Like that's where this refrigerant is at in its condition. And it's going to feed into this evaporator, or into the evaporator chamber. Now, the purge unit has a evaporator coil wound up inside of that big black cylinder, was insulated cylinder that was there. So what happens is, as this hot gas flows into here, the refrigerant in this little purge unit starts to take in the heat from it. Now this is going to be a blended gas, so it's going to have some refrigerant, some non-condensables, and the ratio of that just depends on how severe the contamination is. So as it flows through here, it's going to start to condense into a liquid. Okay, so all of our non-condensables, all of our liquid refrigerant, until we get to the point where it starts to stack up down here as a body of liquid and it starts to drain back out as a liquid. Now, as this begins to condense and then drain, a siphoning effect begins to happen, because then that liquid that's draining back out and flows back to the condenser draws in more gas behind it, and it creates this self-feeding loop of condenser gas and then liquid refrigerant draining back out, condenser gas pulling back in, and the process is self-perpetual, self-generating. As long as we are condensing that liquid refrigerant, we can move liquid through here. That's also very important on this drain line, that it have a proper slope to it, because we have to be able to drain through a filter dryer and back into the condenser properly. So if we do not maintain proper elevation and slope back into the condenser, then we may have issues with this evaporator purge draining down correctly, and that may not allow this cycle to happen properly. Now, as the refrigerant is condensing, our non-condensables are going to be stacking up here, because, well, they're not condensable. So as they stack up here, eventually this line begins to move further down and more stack, to the point where most of this, or a good portion of this evaporator, isn't exchanging heat anymore. It's not taking in heat from the discharge gas refrigerant, because the chamber has so much non-condensables that it's just consuming most of the surface area surrounding the evaporator coil. And there's just a little bit of actual refrigerant stacking in here at that point. What happens at this stage? You'll see a superheat drop, or let me rephrase, you'll see a temperature drop on the suction line. So there's two versions of these purge systems that we'll see in today's systems. Now, the old schools, some of those were a little different. One version that you'll see with Trane is the temperature sensor on the suction line sees that our suction temperature got below a certain threshold. It's usually about 18 degrees Fahrenheit. Once we got below that threshold, it knows that, okay, I'm no longer absorbing heat in this evaporator. I need to begin a purge cycle. So once it commits to that, it opens a solenoid up here, and there's some other solenoids in the process, but it opens this solenoid here, which allows us to draw this pump turns on, opens solenoid, and that atmosphere is drawn off and pumped out of the system. And then from there, we're able to run that purge pump. Now, this compressor never turns off in this process, but as we run the pump, we slowly draw all those non-condensables back off the top of this chamber, and you'll see your purge suction line temperature begin to come back up. Again, once it crosses a certain threshold, then it will stop the pump out process and allow more condensables to stack, or non-condensables to stack in there, until it needs to do another pump out cycle. And it will just do this back and forth process, never turns this compressor off. This refrigerant circuit stays online the entire time. We just cycle when the pump out pump needs to engage or disengage accordingly based off of that temperature. Now, a different way to do this is checking the actual pressure. So as we know, if we have non-condensables stacked in a system, those show up as a higher pressure. They force our refrigerant pressures up from, call it normal or normal saturation. So when that happens, we can compare a transducer that will be on this chamber to the condenser pressure transducer. So in that style, when we see that the purge tank pressure, it gets above a certain threshold of it's just a few psi higher than our condenser pressure, then the system knows that, okay, I've got a large amount of non-condensable stacking in here. It's causing this chamber to elevate in pressure above what the condenser pressure is. I need to go into a pump out. So those are the two ways that modern systems are managing this, whether they're monitoring the purge compressor suction line or whether they're monitoring the purge evaporator chamber pressure and then comparing the two. Either way, I think they're both effective in their own ways. They both have their strengths. They both have their weaknesses. I don't truly think that one is that much better than the other, personally. You can make arguments in both ways on which one could be more effective. Either way, that is how we're managing when the non-condensables are in here. So, because even on the pressure one, once we pump out for a certain period of time and then we recheck pressure and we're back to being below our threshold, and we're equalized on the two pressures, then we know our pump out's good. We just need to continue running the purge system until we are able to stack in more non-condensables, and then if we need to, do another pump out later. There is a key note that I want to make here. I'm very specifically saying non-condensables. Is water a condensable? The answer is yes. We can condense water. So, and it changes with the pressure that we're at, right? Just like with refrigerant. So our pressure matters on where our condensing point is, but we can condense it, and it does. So that's why we need to have a dryer here leaving the purge system. And this dryer has to be routinely serviced at a bare minimum on a tight system on an annual basis. But if we have a system that is having a lot of leaks and a lot of trouble, this dryer might need to be replaced every quarter, or that just comes back to how severe the condition is. And most of the time, these lines will have a sight glass in them, or it's recommended to have a sight glass where you can see the liquid refrigerant physically draining here. But the sight glass also does another thing. It has a moisture indicator for us, and we can monitor that moisture indicator to confirm how dry we are coming, or how dry the system is coming out of the purge system, or the purge tank. So if we're seeing that every time we come look at this machine, we're showing a wet moisture indicator, then it's probably a good idea to start doing more routine changes on that dryer. And that's if we don't expect there to be any leaks. Just because you start to see moisture when you start to take over maintenance, but you can't find leaks on a machine, it doesn't mean that there wasn't leaks in the past, that moisture got into the system and condensed and just never got dealt with or managed beyond that. So that's something I've ran into many times, where the previous repairs, they never did anything to address the moisture problems that were happening. So just something to be aware of. Either way, that moisture is going to get condensed in this evaporator, and it's going to flow down with that liquid refrigerant. It's not getting pumped out with the non-condensables. And that's a really important fact that we need to keep in mind. So routine dryer service, and then whenever we're doing a recovery on these chillers, monitoring for water in the refrigerant is an important part of that process. And that water could be there not from a busted tube, but from excessive pump outs and not maintaining our dryers, keeping the system dry in the process. Let's see. Okay. So we talked through hot gas comes in, non-condensables stack, pump non-condensables out, liquid and moisture condense, stack, drain back into the condenser. We're pulling off of a midpoint in the condenser. We could be monitoring for pump out via suction temperature or purge chamber pressure compared to condenser pressure. These levels fluctuate accordingly based off of how much non-condensables we're stacking. If there's very little non-condensables, by the way, this purge system could run for days and never need to do a single pump out. If the system is clean, it's tight, it's not having leaks, we don't have any contaminants in the system, that's great. Having a pump out is a good thing, right? Not having pump outs is a good thing. We want to try to avoid that as much as possible. Let's see. So the purge compressor never stops during operation. Right, unless it is physically turned off. So you can go in and manually turn off the purge compressor when the chiller is on, But other than that, yes, just about any mode that you would put it in, it's almost always going to be running, unless it's in like an adaptive mode, which is a separate conversation. So with all these negatives and extra requirements for low pressure chillers, there must be a huge advantage compared to high pressure chillers, right? What exactly is the benefit? So low pressure machines have we can achieve some really good efficiencies. The refrigerants themselves are relatively cheaper. Um, I think the biggest thing that comes to mind is the efficiency aspect. Like we can I'd have to look up the actual, like the BTUs per pound metrics and being able to move that refrigerant, but it, from my understanding, like it's really good compared to high pressure machines. Well, when we say less pressure, less work, on some scale, we can. Our vessels don't have to be rated for as high of a pressure. That is true, but we still end up operating within the same horsepower workloads. So, like our lift, for example, our lift for when we look at it from a saturation perspective, our lift for low pressure machines is about the same for what it would be for a high pressure machine from a saturation perspective. So when we start exceeding, say, 40 to 60 degrees of lift and saturation, we could start pushing into surging issues with a low or high pressure machine, as an example. So while the physical pressure lift is different, the molecules are also different, and the chiller is designed accordingly. And the better thing maybe for me to say is I don't have the best answer for that. I have thoughts, like I'm sharing kind of my thoughts and theories around it, but I don't have the best answer that an engineer might provide. They may have something far more clear and concise on, oh yeah, low pressures have XYZ. And that is actually a really good topic to look into. Um, that may be something I look at doing. I may look into a little bit deeper as to why are low pressure favored over high pressure. From my understanding, not to push back on you, but my understanding is not as simple as it's just because it's lower pressure, it's less work kind of benefit, because it's not the horsepower required to move that refrigerant, like it's not that straightforward of a solution from my understanding. I could be wrong on that. I could absolutely be wrong on that. Now, we haven't covered a regen tank. Now, before I dive into the regen cycle, I mean, do we actually want to get into that part of it? Because I could spend another 10-15 minutes explaining the regen. But if it's not really needed, we can move on into other questions. Y'all can tell me which way you'd like to go. Do we want to cover the regen cycle and how that works with the carbon tank, or do we want to move on? White collar striking. You know, the low pressure stuff's been around for a really long time, though. Uh, like a really long time. So there's absolute solid validity, um, to having low pressure equipment. I Like I said, I really should look into this topic and try to give some feedback. Because it is I will admit, I've not taken the time to, or at least if I have, I don't ever remember looking into just why do we find low pressures so much more superior, that we would push so hard to have them in the first place. So other than just having my ideas, my thoughts in my head, and just from what I see and understand. All right, so we never heard of a regen. Okay, well then let's just get into it. We're here. We've covered all the bases you need to understand. So let me draw the regen tank. Move this. If we come over here, and then we need, we'll stick with the same color scheme. Comes over here. This come out here. It's going to go this way, this way, this way. How you doing, Michael? Good to see you, bud. With the RTH pump out cycle, it's always a fun one. RTH. Okay. So, let's talk about a regen. So, I need to draw one more line in here. Not that way. What we're going to do is we're going to add, actually, let's do this. That way, solenoid, get the solenoid. Hopefully you're liking my artwork today. Regen. I'm very proud of it. I'm actually quite impressed by what I've created here, I will say. It's not my greatest. It's not, you know, whatever the artists are that out there, but you know, for a wrench monkey, I'm happy with this. Okay. So a regen tank. This is it is an additional cylinder that is attached to the Purge assembly. All this is built in. And you'll see this on newer machines as of, let me think, it was either 2002 or 2012. I forget which. Somewhere in there. You start to see these tanks come into effect. And the reason for that, when we are doing a pump out, we cannot isolate the discharge gas, the high pressure gas that's in here, refrigerant, from the non-condensables. Now, sure, we can separate it as it condenses as a liquid, but all the stuff stacked up in the top here, there's still refrigerant in that non-condensable. So, when we go to do a pump out, the refrigerant gets drawn out with the non-condensables. Now, it's a fairly minute, at least in my understanding, it's a fairly minor amount of refrigerant, but it's refrigerant nonetheless. And regulations have gotten really strict on this stuff. In addition to that, refrigerant has gotten so expensive and whatnot, like if we don't have to just lose it, it's better that we don't. We can recapture that, and we're not adding whatever pollution to the environment per regulation. So, drawing off of here is a blend of non-condensables and refrigerant. Mostly non-condensables, a little bit of refrigerant. As that pumps out, we pump it into this other tank. This tank is full of carbon, little carbon modules. I've actually opened these up before. It's little black pellets is the ones I've seen. That's what they look like inside of there. So these black pellets of carbon, what they do is the refrigerant molecules will bond to them. So basically it's filtering out the refrigerant from the non-condensables, so that the non-condensables, you know, the nitrogen in the atmosphere, will flow past the carbon and flow out. Let's say this is out to an atmosphere rejection. So there's two more solenoids down here. We'll explain why in a moment. But there's one solenoid for the pump itself, and that pushes into the regen tank. And then from there, we push through the tank and out into this solenoid or this one. This one here we're going to call our standard outside air pump out. So once we process through here, ideally we have a pure non-condensable gas leaving this solenoid and moving back out into atmosphere. And this tank is able to run like that. I mean, it can hold it can run for quite some time, a lot of pump out time before it actually needs to go into what we call a regen cycle. So the mixture comes off, pumps in, refrigerant gets captured by the carbon, non-condensables continue flowing out, rejected out. Now, there's this extra piece here. This is a heater. So normally this tank is just going to be at your plant temperature, right? So we're talking, it may be 80 degrees in a plant, it may be 100 degrees in a plant, 120 degrees in a plant. It's going to be whatever the plant temperature is either way. So that's the standing temperature of this tank and the carbon that's inside of here and whatever's processing through. At some point though, we want to capture that refrigerant back out of this tank and get it back into the system to be usable again. So to do that, what we end up doing is we actually we close this valve to reject to the outside air, and we open this evaporator valve. And if memory serves, yeah, we should not run the rest of the pump out assembly. We don't need the pump. This will stay closed. All this remains. The only thing that will happen here is we will keep the which this valve here to the atmosphere only opens during pump out anyway. But this will stay closed, and we open this valve. This valve goes back to the evaporator. So this only works when the chiller is online and we have our evaporator process down. So what happens is this heater turns on. So this is a electric heater submersed into the carbon, and we're heating this carbon up. There's also a temperature sensor in here. So we're getting the carbon up in temperature in order to release the trapped refrigerant out of it and allow it to be drawn back into the evaporator. That is its purpose. And I think this heats the carbon up to, is it like 145? I think is the metric. I've got my let me pull it up. I've got my text sheet on this. Or my troubleshooting guide. CVH. Let me see if I can find it on my phone. Nope, not that one. That's what happens when we got too many. Here I am getting off in the weeds. I'm pretty sure it's 145. It's the temperature that it triggers at, or it builds up to. Come on. There's a YK. There's a VRV. Where's my train? Dang it. Either way, I'm not gonna kill a bunch of time on it. I just need to have those printed and just sitting here so I can just whip it out and go, oh yeah, it's right there. Yeah. I think I've said this multiple times. I haven't done it yet. Either way, it should be like 145. That is the set point we're getting to, that by the time we hit that temperature in the carbon, we expect to have gotten all of the refrigerant to release from the carbon and allow it to be drawn back back into the evaporator. That is our ultimate goal and focus. And this heater accomplishes that. And once it's done with the regen cycle, this valve closes, heater turns off, we can go back into a normal purge operation. But that is this tank's sole job. Capture that refrigerant via the vapor. It acts like a filter, a refrigerant filter for the non-condensables leaving. But then we can draw that refrigerant back in once we've on occasion, in order to keep that refrigerant in service and not let that refrigerant just get escaped out into the atmosphere. Semi-annual maintenance currently. Putting in my lunch. Jimmy John's. We're glad to have you, Michael. Good to see you, bud. It's better than contemporary art, I'd say. Literal banana, yeah. Yeah, it's true. I appreciate your compliments, guys. I like my artwork. I'm gonna be a happy guy today. It's good. You guys. All right. Yeah. That fly is. He just wants his spotlight, guys. I give him a break. He wants his spotlight. Okay. Getting back to the original question, train chiller purge explanation. That is a full rundown of a train chiller purge, from how do we even define a purge, where is it used, how is it connected, and how does the internals work from a basics perspective, and then following that into the regen cycle itself. There's a lot to it. It's a fairly extensive process. I just ran through a lot of the high level stuff here. I didn't get into every little detail. I did cover a lot of it though. If you're in the certification course at Chiller Academy, I have lessons on this. I also go deeper into the refrigeration cycles and the non-condensable side of this and low pressure. Like, I cover all of that stuff in more detail and in a more structured way than what I had here. So if you are enrolled in that, go back. Most of that's going to be in the centrifugal module, so you can go into that module, review a lot of this information there, and just spend more time on it, right? Outside of just this discussion here, and that will really help you get more familiar with it. The more you've had it explained to you, the more I can say it in maybe slightly different ways each time to make it easier to understand and to comprehend, the easier it will make this entire process and help it stick for you long term. Like, it'd be one of those things where you just walk up, you see it, you understand, you're not having to think through it. And that's really a big goal that I think starts to separate the experienced from the new in terms of working on this stuff. You just walk up, you can see, and you understand. You know what you're looking at, and your mind already has that picture built. You've already got that infrastructure in your head built. And that is something that, like, I've thought about doing even here on stream, of taking, okay, let's identify these components, or you can just show me a picture of just about any chiller, even if I haven't seen the chiller before. And I could start to identify to you fairly quickly, and give me just a couple of minutes of just looking at it. I could tell you exactly how they're trying to operate just based off of the design of that chiller. If they have any hot gas bypasses, if they have an economizer, what type of economizer, what type of metering device, what type of metering controller they're using, what type of evaporator. Like, there's so many of those details that you can identify without ever having been trained on that machine. And if you know the basic principles of how that component is meant to function and how it plays a role into the broader machine itself, then you can very quickly begin to deduce, okay, this is what I should expect this thing to see. These are some general numbers that you would typically want for this scenario. And at that point, we continue with the troubleshooting, right? That is that is a goal that I would try to set. But to do that, you have to spend enough time on the material. You have to have it explained enough times the right way. You it comes back to your willingness to study that topic and really become familiar and proficient with it. But when you can do that, like, you can save yourself a ton of time on site and really show a lot of competency, because you're actually able to just look, you see, you understand, and you can just start moving through that. Whereas if you don't understand all these components and these systems, that's okay. All of us started there. But when you do walk up to a machine, now you're spending a lot of time trying to analyze, okay, this was, I think that's a that, I think that's a that, these do this, and when you put them together, like, it takes time to build that into your brain for your troubleshoot. Whereas the more time you spend on this, the more you practice processing, this is what this thing does. Whether it's in front of you or not is irrelevant, in my opinion. It doesn't matter if you're standing in front of it. It matters that you're mentally exercising that part of your technical skill set. And if you can do that, then when you do see it on site, you can much more quickly adapt your mind to, this is what I'm working on today. This is how this should function in the system. I don't have to read the entire IOM all over again to remind myself. I've already got it to memory, but that takes repetition and time. My point being, if you're in the certification course, this is a good opportunity to go in and spend some more time on that and really get this repetition down for yourself. I do see your question there, Archer. Let me just kind of go through some other things. I have a question on chiller service team and a BMS commissioning team. It's different nature of job, but what details does the service team give to BMS team for train make? Okay, so John, it's a good question. Let me get it pulled up here so everybody can see. Okay. So, in terms of the chiller service team and commissioning, one of the things that's really important in terms of being able to work together is understanding what the scope and the objective is of the machine, which comes back to what it was designed for. So it's important that, like, if we have a set GPM and the automation system, the BMS, so building management system, if that controls team is having a variable loop of any kind, right? They need to understand what your flow requirements are, either from a DP perspective or a GPM perspective if they're using a flow sensor. Those things have to be communicated back and forth. And while we as the service team or the chiller service team might have that data for that chiller, the automation team may not have that. It is essential for us to communicate those things. Typically, from a communicating to the chiller perspective, most of the time the BMS techs are able to go up to the chiller, wire up to it, get the BACnet or Modbus communication network going, whatever that stuff is, and usually they're pretty good. They can go pull their own points and they know what that chiller needs from a communications perspective. So in my experience, I'm typically not having to do that much of that part of their role for them. Where I'm having to work with them is, okay, how are we controlling this machine? How are we going to stage it? How do we expect it to run? Are we going to do a lead lag type of system, or are we doing balanced loads? Do we have headers? How are we running the pumps? You know, the mechanical aspect of this, of how are we staging? These are the minimum requirements that this particular machine needs. Like, that's what we're working through together. So from a train, we have a couple of control panels. So you could be dealing with a CH530 style panel. You could have an older machine with a UPC2 still in it. You could have a train TU, right? So you could have a couple of different panels in there. So I'm just trying to think of it. What are some specifics that might go along with each of those that they would want to have, other than just like a points list? But typically, most of the automation guys I've worked with, they can usually get their own points list. I haven't had an issue with that. To even get that list, though, you've got to get a manual on the control panel itself. So they've got to be able to pull that list in, and then you've got to have the right manual that has that list of points in it, to where they know that, okay, this control panel has these points that I can pull on the automation side. And if you don't know what I mean by points and protocols, BACnet, Modbus, any of that, that's okay. We don't have to dive into that right now. I do have lessons on that in the academy. So if you're in the certification course, go to control panels module. And in that module, I'm going to have a lesson on protocols. I'm going to have a lesson on, the protocols will actually cover like BACnet, Modbus. I should discuss the points in there that they're going to pull and use to, communicate with the chiller. All that should be in that module, and you can reference that there. So I think that's the main thing that I'd be focused on between the two teams. What is how you're staging the equipment? Is how they expect to do it going to line up with the chiller? Because not every chiller does it the same way. And if they get the timing out of sorts, then it's going to cause alarms to trigger at the chiller. Like for flow, for example, if they're controlling the pumps external from the chillers, there's some of these chillers will have an alarm that if it sees flow, especially some of these air-cooleds, if it sees flow before it gets the call to turn on, then it will identify that as a possible failed flow switch, because it doesn't want to see flow until it gets its own command on first, and then it can see the flow switch turn on or establish flow, and everything start normal from there. So if it doesn't see that, those can give alarms. And if the automation tech doesn't know that, and he's trying to go through a different control sequence there, well, then he may try to bring the pumps on prematurely, trip the chiller out on alarm, and now like we've got a whole process that we've got to work through. So staging, if they're a variable flow, what are our flow requirements for this machine, things of that nature. That's the main stuff that I'd be worried about them communicating. Let's see, Castrol view. Chiller. Yeah, on the Kestrel view question, Starlord. So Kestrel view it's just a different control system, from my understanding, and let's see, making sure I'm not getting my names mixed up. Yeah, so it's That's what you'll see on like smart chillers, for example. You'll see Kestrel view. Man, why am I feeling like I'm getting my names mixed up here? We've got MCS, Kiltex. I am getting my names mixed up. Kiltex. I'm thinking of Kiltex, not Kestrel. Never mind. Yeah, I see that Mashak has already responded there. I'm not overly familiar with Kestrel personally, so I could tell you about Kiltex. That's why something just was telling me something in your brain ain't firing there. That's what it is. I was thinking of a different panel. Anyway, I would go with what Mashak said. Thank you for answering that, sir. Okay, so John, so only operational logic to be explained. Rest of thing BMS team will handwrite. Yeah, exactly. So they, as long as how they're trying to control the chiller is okay with the chiller, and they don't always know that, that's where our role comes in. So that's the communication we have to have, and then it comes back to testing that with them when they create the logic, write it all out, do their thing. Let's put the plant through its paces. Let's let it stage up, let it stage down. Let's see if what they wrote is going to cause us any trouble with how the chiller is trying to cycle on, off, control safeties, the whole bit. So that'll be the main thing that we're trying to pay attention to and communicate back and forth. All right. Question: do you think centrifugals are kind of getting out of fashion now with a new variable speed screws and all that? Turbo cores are I think the older style ones are fading out of favor. I'm reading up on some of these on the comments here before I will get to your question there, Sterling. Faster impellers, mag bearing. Traditional ones, the big ones, the fatties are getting phased out by the younger, skinnier ones. Maybe those big are freaking tanks. Turbo core because electronics are just too sensitive. Snowflake. Oh man, you guys can see each other. Sterling, be nice. Let's see. Okay. Yeah, I've got some thoughts on this. Let me get this up. I'm not posting everything you said, Sterling. Okay. Do you think centrifugals are kind of getting out of fashion now with the new variable speed screws and turbo core efficiency and all of that? My short answer is absolutely not. Now, let me give some context there. A lot of it comes down to scale and size. One, screws can get pretty large, but screw compressors have a scale limitation. They can only get so big before they just cannot compete with a centrifugal and how much refrigerant they can process through them. So then we get into a scenario of they can only go so big, but then we have to have a lot more of those chillers running simultaneously. And another major issue with screws is the vibration. Even with the variable speed ones, which tend to do fairly well, they have a huge amount of vibration, and that creates a lot of structural resonance that just, again, it can create problems if not properly managed, and it takes a lot of footprint space. they can just only go so big and be economically viable, is my point. Now, on the same token, turbo cores, which, as it was pointed out, yeah, they are centrifugals, and you know that, but turbo cores are, um, they only go so big as well. Those compressors are not built, and I don't think Danfoss had the intention to making them scale to the sizes that we need many times in this industry. When we're talking thousands of tons, turbo cores, it takes way too many of them. Even the TT700, which is their largest size, it would take several of those to do what one compressor could do. And then you think we have issues with just the chillers we have today, which might have 2, 3, 4 of them on there. Let's try scaling that into a dozen of those freaking things on one machine. Like you see that with some of the smart chillers that we see that are turbo core modules stacked together and stuff. I mean, they're a nightmare. Versus we just have one standard machine. Now, again, what I'm hitting on here is scale of this. So, do we see on a smaller scale more of these like we have really good screws today and machines like a turbo core? Do we see more of them? Absolutely. Will we continue to see more of them? Absolutely. I think so. The days where below 500 tons, we had these, like the CVH and the YKs of the world and all of that happening below 500 tons, I think are coming to a close. They're still happening, right? There are still, say, 400 or 500 ton centrifugals getting pulled out and another full-size regular YK, CVH, whatever centrifugal getting put back in its place. It is still happening. But a lot of these shops, a lot of these salesmen are selling to the customer these smaller, more modular style packages. They tend to be cheaper. They have really high efficiency ratings. And a lot of people are pushing this efficiency thing. And so these mag bearing machines, when tuned and running correctly, can achieve those without issue. The problem is when running correctly is the main caveat there, and that's a whole nother topic of conversation. But yeah, and I would say, okay, there's a future where you could argue seeing 750 to 1,000 tons on some of these machines, where we may build them more modularly. We may scale them into where we can stack it all together and we're producing maybe screws, but even for sure these little small mag bearing centrifugals up to 750 to 1,000 tons, something like that. Are those compressors, and does it make economic sense to scale beyond 1,000 tons for those? Not that I can tell. Even getting above 500 tons seems questionable, at least at the moment. And I think that's why we see the split in the barriers. Now, that comes back to what size systems do you see on a routine? So if you're working in that less than 500 ton segment of the market, and that's almost everything that you see, then in your world, yeah, you're gonna start to see that. You are seeing that transition, you are seeing that movement, and this is just this is what you're gonna have to work with. It is what it is. The customers, the salesmen, the manufacturers, they're the ones that ultimately pull the strings to make those decisions happen. It's our job as the technician to just make it function for the customer. That is our ultimate goal. That means we have to be knowledgeable and trained and just willing to step in and do what we got to do. Everything's going to be hard, right? That's one of the big things that has been a very valuable lesson that I've just kind of taken into my life. It doesn't matter what you do in life. It does not matter. I was having this conversation with a young guy the other day about this. It absolutely does not matter what you do. Everything in life is going to be hard. So you might as well pick the hard things that are long-term worth doing. It doesn't matter whether you're going to be a baggage boy at a grocery store, an auto mechanic, you're going to go work on chillers, you're going to go work on RTUs. Every freaking thing that we have in front of us is going to be hard to do, period. There's going to be things we might not like. So we might as well do what we do enjoy, or get proficient enough at them to enjoy it. I personally absolutely love turbo cores, right? I do. They have a lot of problems. They can be really difficult to work on at times, and be confident in your diagnosis. That's the big thing about it, is with these electronics, sometimes we just have to rule everything else out as best we can, and then just take a shot and hope it's right. And that's just how it is. But for me, I did that enough times over a long enough period of time. I'm okay with that. And I've been wrong enough times to learn from it. I've also been right enough times to see what I did right. And I'm okay with that. I've blown up my fair share of these compressors, and I've also saved enough of them. So, I mean, to give an example, the first DMAG that I came across, so shaft demagnetization, where these are permanent magnet shafts, and they'll lose some of that sometimes. And when that happens, the bearings can't control the shaft, and the compressor's done at that point. But holy freaking hell, is it hard to troubleshoot that, especially in a time where I was finding that as Daikin was just developing its DMAG literature, just to kind of paint a perspective, right? So there's a lot of things that we are frustrated with them because they're hard in the moment, and it's okay. I don't think that's a problem. But if we really put the effort in, as we get better at it, it'll become less hard. Or we will at least hate it less. I'll put it that way. Now, I'm not speaking for you. I'm not saying that you specifically will fall in love with turbo core with just given enough time. I'm not saying that whatsoever. And I'm not saying they're the best thing on the market. They're not. They've got a lot of problems. I am trying to give some perspective and encouragement on it's what makes us who we are and why we do what we do, and why so few other people are doing it. To me, it's a comforting thought. Yeah. Sorry, not trying to get too off the rails there. Kind of getting philosophical on some level, but to summarize the question, below 500 to 1,000 tons, they are, because of efficiency and cost, you're going to see a lot less of traditional big bulky centrifugals. You'll see a lot more of these newer styles of machines. But once you get above that scale, you're back to the traditional centrifugals, because there's just nothing that's been developed that can compete with that side of the market. And a screw compressor does not have the ability to scale to that tonnage and efficiency. It just does not make economic sense to build a screw compressor that big, because we have centrifugals. And centrifugals would just own it every day of the week. Doesn't matter mag bearing or oiled, at that scale, right? At that scale. And we are seeing that mag bearings are now competing at that scale. What the YZ by York is I think goes up to 1,500 tons now, which we've already had the WME by Daikin. Those, I think, start off, or those can go up to 1,500 or 2,000 tons, somewhere in there, right? So we have mag bearings that scale to that size. And they're going to continue to figure out how to build these machines to scale bigger and bigger, because the top end of what we see in mass production is between 500 tons, or 5,000 tons, I mean. 5,000 tons is about the standard top end, but there are machines that have been built up to 8,000 tons. I think the largest machines are like 8 to 10,000 tons, but those are specific built for those purposes. Those are not considered a as much as you could call it a factory package, if you will. Most of your factory determined packages, even though it's not that simple, cap at about 5,000 tons right now with what we have in the industry. And that's what you'll see on these major plants, airports, municipal districts, things like that. They flip-flops. What, the compressor or Gen Z? It'd be nice if the compressor would, wouldn't it? Get that big heavy thing off of us. Oh man, okay. I've got a couple of minutes. If somebody does have another conversation topic or a chat or something, I will take it. Otherwise, we can start to come to a conclusion here. What else you got? I will say that I have gotten some feedback on the simulator, the chiller service simulator, and the tutorial is way too complex. I'm really working to get it revised and put a easier to follow tutorial in. I know a lot of you have gone through the tutorial and it's just very overwhelming, especially not having prior exposure to chillers. Completely get it, because part of this simulator's goal is to help you. Like, you don't have to come in with experience in order to understand the chiller service simulator. Like I want to build it in a way to where you can just come in with little to no experience, and then be able to understand, follow along, and start to build that experience for yourself. And that the Hopkins Center, as I called it, or Hopkins facility, with the centrifugal plant that I made with the headers, like, it's just way too much to represent that. And the very first plant you come into, which is warehouse 12, once you get into the paid section, it is not that. It is a very, very simple 2 chiller air cooled little small RTAP, not RT, 30 RAP carrier air cooled chillers. It's very, very simple. So like, that is the actual starting point. So I'm actually rebuilding the tutorial, and it's just going to be a simple air handler and an air cooled chiller that are going to run in unison, just to give you a feel for the plant and really help you get an introduction to some of the terms and how it's laid out. I'll let everybody know once I officially have the new tutorial launched, and it'll give you an actual perspective on what it's going to look like once you get into the paid side of it. Something like the Hopkins facility is going to be way down the road into the simulator as it's getting built out and getting more complicated as we go, because it was an intermediate plant. It was not the right move to make when I built the tutorial. So I do apologize for that, and I know that was a pain. I do see, Michael, you said SCR temp showing negative 76 degrees. Now, SCR on a turbo core? SCR on a what? Let's see. Oh, yeah, you said you got three turbo cores. Well, have you verified the temp sensor? So that sensor is up there underneath the SCRs on the block. So did you verify the temp sensor itself? Which you can measure that inside of the backplane. So if we come over to, let me pull up a picture here. Let me get my Let's see. Is it this one? Right there. Let's see. Motor. It should be what these interiors, I think. I don't think anyway, you got this section of plugs up here. And this should be going to the actual motor, like stator temp sensor. And then the inverter and SCR should be, I think, this one here on the back plane. So you can verify that sensor here before you go all the way around. And the manual should have the temp chart. You can reference that. So I would check that personally. And that sensor should be replaceable. Yeah, that sensor is replaceable in the field. Like I said, it's right here. I guess we can. Let me pull up where that sensor is located. Yeah, the sensor should be somewhere right in here. Which right? Is that right? Is that one it? That might be it. That might be it right there. I've seen some of these have a slightly different design. It doesn't look quite like that, but yeah, the sensor for those should be right in here. So this is where you'd be looking once you pull the back plane off the top of it and you dive in there. Do you think I can get a good turbo core with the Danfoss manual only? Yeah, absolutely. You can, well, so there's two ways. One, you just send me an email. I'll send it to you. Or inside of the Turbo Tool app. So let me pull up that app. Okay. So right here, this is the Turbo Tool app by Danfoss. If we come over to Documents and go to Manuals, we have the service manual. Like this is Danfoss's actual service manual for this, and you can download it. Now, I say this, I don't know if this is available in the UK, to be fair. So if this is not available to you in the UK, just send me an email. I'll send you the manual. It's not a big deal. So we can, yeah. And there are multiple manuals. So the manual they've got in the app is the basic one. There actually is other advanced manuals, by the way. So just we can work through that. I can get you the manual so you can read through it, brush up on it. If you can get this, so here's the other thing. Talks about in terms of like getting familiar with the verify documents. Yeah, videos. All these videos here, which I'm pretty confident Danfoss has these videos on YouTube as well. Like we've got a whole bank of them they've built in at this point to be able to like show you how to do service and everything on these compressors. So I really feel like Danfoss has done a lot to make servicing the turbo core as easy as they can while still operating within people's skill sets at the same time. Fancier, classier ones with the comfort. Train liquid level sensor functioning process. If you can explain in short. Sure. Yeah, we can do that. We can make it real quick. Okay, so train liquid level sensor functioning process. Now there's two sensors that Train has produced. There's the older one and there's the newer one. So the older one, so you've got the sensor chamber, the actual module head is in the bottom down here, and it's got a pigtail that comes off. And then there's this rod that sticks up inside. And around that rod is a magnet. What color? We'll go brown. So there's this floating magnet that sits in here and floats up and down based off of the liquid refrigerant level. And that's how it's sensed. So the way this works, this is going to be on the evaporator side specifically, because they're using this for metering valve control. So on the bottom of the evaporator, we've got a line that comes off, and then up here, this comes off, goes back to the top of the evap. So bottom of evap, and then top. So yeah, liquid refrigerant comes in. We have a vapor relief up top to allow that liquid refrigerant to equalize in here. So as it equalizes, it's able to adjust up and down, and I think these show in inches, you know, how far you are from set point, so 0 being the neutral. So yeah, so this is, as this magnet moves up and down, it has a sensor on this stem of the module that is able to detect that magnetic field, and that determines what the actual liquid level is in the evaporator, and then it will open and close the EXVs in order to adjust this level. So if we're starting to get too much liquid, it will close them down. Liquid will begin to fall. If it has too little liquid, it will open them up and push more refrigerant into the evaporator in order to control this. Now, one of the major things that will negatively impact this is oil. So if we have a heavy oil latency, or let me use basic terms. If we have a lot of oil stacking in the evaporator, that oil creates a lot of extra foaming action. So what can happen is this whole top section could have a whole layer of foam form on top, and that layer of foam will push that sensor up higher. So it's actually up above where the actual liquid level is, but it doesn't know that. So what it ends up doing is it causes the EXVs to run the evaporator low on refrigerant, and that affects approach values. In addition to, you've got a lot of oil, so that's already reducing approach, so like it double compounds the issue. This is a major issue with these sensors, and why they were such a pain is if you didn't control oil in the evaporator, it threw the sensor out, and it just caused all kinds of freaking havoc on controlling the liquid levels in the evaporator. So Trane, their newer styles are using a I don't have it in here. I do have one of those sensors, but it is in my storage, and I haven't set up my little props cubby yet. Anyway, the new sensors don't have the float. Okay, so they're just strictly a electronic sensor. And Trane does say in their literature that they are designed to calibrate for continuity differences between oil and refrigerant. So the sensor is able to take the readings, and it can determine, okay, this section right here that I'm reading is actually, that's coming across as oil instead of actually just liquid refrigerant standing there. So I'm going to ignore that. And down here at this line, I see actual liquid refrigerant. So I'm going to pay attention to that line and not this one up here. It's not perfect. But it does a much better job than the original sensor, which had just the float that would float on top of the oil. And yeah, so when you work on these, there's no mechanical motion here. So the older ones, like if you shook them around, you could hear the float in there clanging around. But the newer ones don't have any of that. They're just the probe that makes contact with the refrigerant and senses where the level is. But everything else in the process is still the same. How it reacts to the EXVs is still the same. All of that maintains. And we can look at a couple of pictures of that. So, oops. I can come over here to my screw diagrams. Let me find a picture we can actually, I can show you what this looks like on the machine. I find the one I want. I can't find it fairly quickly, I'll just move on. But all right, so here's the EXV block, right? So this has two EXVs in it because of just capacity, right? So instead of having one huge EXV, we can split this in half and still maintain full control and proper flow through the EXV block without having to just have a massive valve that's hard and expensive to replace and build and manufacture all the things. So this would be your EXV head. This is a common thing you'll see in chillers where they'll split the EXVs into multiple heads on the same block in order to achieve that flow. And then let me see if I can find the actual level sensor, just so we have a visual representation of what we're discussing. Again, if it's not where I'm thinking it is, I'll just move on, but it should be right in here. The one I'm wanting to show you. Not that one, not that one. Where are you? It's not exactly the one I'm trying to show you. Yeah, you can't really see it in this one. So the sensor is down here in this corner. You can see this line right here coming up. That is the vapor valve coming back off the top, and then that is the bottom down here is the liquid coming into that sensor, and that cylinder is just right there, right? You can kind of see the top of it right there in the picture. I have another picture where I've got a close-up of that shot. I just don't, I'd have to spend some time just kind of trying to dig for it, but that is the basic process of how that sensor works, what it's controlling for, and if it sees positive inches, levels high, negative inches, levels low, adjust the valves accordingly to get that that level where the chiller actually wants it to maintain. I had one training session on turbo core, but they kind of said basically if you have an issue, go to the manual, follow the troubleshooting guide. That's about it. I mean, yeah, in fairness, there's so much to these compressors. Like, it is really hard to give a proper class, especially if they're not familiar with it enough themselves. Like if they're just instructors, but they've not done a lot of hands-on time. Yeesh. Do you go over the SCR temp showing negative 76 degrees already? Dustin called me and ruining my training. Let's see. Did you go? Well, I just talked about where the sensor's at, and then trying to verify it through the backplane. So if you can read it through the backplane of the module where it plugs in on the Molex. I talked about that earlier, yeah, if you missed it. Check the sensor first. Yeah, so I'm in Texas. I'm in Texas. I see you say you're in Dubai. Welcome. Just getting my chiller career started. Started with JCI, super pumped. Got any tips for a guy getting into chillers? You're being with JCI, you've got a really good internal training network with their modules. I don't know if they've got you set up on that yet, but that's something I would definitely take advantage of. It's an internal to JCI only. That's not something they have open to anybody else. Like, you've got to be a JCI tech, and even then, like, I know you've got to hit certain wickets to have particular trainings available to you. They don't have the entire library that they have open to everybody inside of their own network. So they do still kind of gatekeep that to a degree. It's not less of a criticism, more of just a heads up if you haven't been shown or told anything about that. let's see, really getting your fundamentals down, right? Which is what my certification course at chilleracademy.com is all about. Like if you're in there, really work on your fundamentals. I love York machines. I think the machines are great. Um, there's a lot to it though. Even their air cooled, like their air cooled are not simple. Well, I say that their was it the YLAA, like their scroll series aren't too bad. Those are fine. But when you get into their screw air cooleds and then eventually their centrifugal air cooleds, they're not simple machines. And then their water cooleds are not simple either. Like they're just, York does a lot to try to push their limits on efficiency, and that's a huge selling point they try to drive a lot. So your ability to tune a machine is gonna matter, and that comes back to just raw understanding. How well do you understand these concepts, these principles? How well can you implement them? And that comes back to time spent just working through it. How much time are you spending studying, being focused on it, and getting your head around these concepts? It's a lot of the same stuff you already know, right? It's a lot of the same basic principles of how HVAC systems work, but it's done at a larger scale. That's the big thing. Don't approach this from a perspective of you've got to learn something completely new. We're still using refrigerants. Doesn't matter if it's low pressure, high pressure, all that, regardless. It's a refrigerant. It has a saturation. We're exchanging heat into the day. Instead of moving instead of moving air over a coil and an RTU, we're now moving water through a heat exchanger. Same process. GPM is equivalent to CFM in terms of a concept. If the symptoms you expect to have with low airflow, low CFM, are the same symptoms you would expect to have with low water flow, low GPM, right? All those concepts are still the same. Superheats work the same. Subcooling works the same. But it does get more complicated. Our controls packages are more complicated. That's just because we're doing more with the system we have. We're trying to achieve something on a much greater and larger scale. That's what this comes down to. So you're not having to relearn your industry, but you are having to step it up into a much higher level of where your industry operates. That is the difference. Like I said, York has some great internal resources for this. Utilize them. And then if you're needing help beyond that, that's where the Chiller Academy comes in. That's why I've built this. I have a lot of JCI technicians in the academy. So, like, just something to consider depending on just how it's going and how serious you want to take this, how quickly you want to move. That's what it comes down to. Anyway, let's wrap this up. Y'all have a wonderful day, a wonderful week. I do plan to see you next week, and life happens, but that's the plan. MTT, make the time for your family, for your spouse, for your kids. They really need you. It is important that we really focus on supporting them as they support us through our busy seasons and all the trials and troubles and tribulations and everything that we go through as field technicians. It's a hard life. It's hard on them just as much as it is us. Let's just try to remember to make some time for them too.